Okay, let's get started. So in the last class we looked at the Low-Reynolds number formulation, and we see that the near wall dependency should be consistent between the model terms and the exact terms. And for that we introduce what is called a damping function into the eddy viscosity formulation. So that is present in the model terms, and therefore that will become consistent. So the damping rates will become consistent between model and exact. Today we will see what boundary conditions we have to apply when we use Low-Reynolds number formulations. If you recall wall functions, the boundary node or the not the boundary node, the first node that is above the wall was placed far above the wall, that is above y plus 30, and it can go up to, let's say, y plus 200 or 100, and there we gave a boundary condition. Okay, so the wall effect was displaced away from the wall. But in the Low-Reynolds number formulation, as I mentioned, you need to resolve the wall. That means you need to have enough mesh points so that you capture all the near wall effects, right? So you will have many points closer to the wall so that you capture all the effects. Okay, and I did mention the first, this is the boundary node, then the, let's call this P node here, right? So this is the south, this is the north. So the P node is the first node above the wall. Okay. First node above the wall, and this must be, as I said, y plus less than or equal to 1 for the P node. So it has to be in the linear sublayer, and many nodes in the linear and buffer layer. So we will see what conditions we have to give when we resolve such a condition. Okay, so the velocities are all straightforward, right? On the wall at y equal to 0, if this was your y direction. Okay, at y equal to 0, that is on the wall, you can specify your velocities to be 0 coming from your no slip and kinematic boundary condition. And what do you do for pressure? Pressure boundary condition on the wall. This must have been taught in the CFD course. Is pressure known to you? No. Then what do you do? Yes, you set a Neumann boundary condition, right? So the velocity, you have a Dirichlet condition, right? For the pressure, it's Neumann. So this is your Dirichlet condition, right? For pressure, you give dp dy here. If you have a curved surface, then it's dp d eta, where eta is the wall normal direction, equal to 0. This is your Neumann condition. So this will update the pressure on the wall, right? So let the flow compute, and it will get updated. This is fine. So now you are computing not just the flow, a laminar flow, this is fine, velocities and pressure. So now this is mean velocity and mean pressure gradient here. So that means there must be a fluctuating or turbulent component that we are computing using k and epsilon. So we need a boundary condition for k, epsilon, or if you are computing omega, and so on. So you need a boundary condition for these things as you resolve the wall. So let us see what they have to be. So k on the wall is straightforward also. So this is not a problem. So k, what should k be on the wall? K has to be 0. K is 0 on the wall, right? It is made up of fluctuating velocity components. Velocity goes to 0, k goes to 0. Only epsilon and omega are something you have to think about it. Let's go back and see what we can do for epsilon boundary condition. Okay. So wall boundary condition for epsilon. So if you recall from yesterday's class, epsilon had no y dependency, okay, no y dependency in the near wall region. This of course to first order, right, to first order. All the terms that we discussed yesterday were first order, we dropped the higher order terms. So to first order we have epsilon having no y dependency in the near wall zone. But we have seen from the budget, if you recall, I did mention what is called a budget, where we saw the data for, let's say, the turbulence, the production rate Pk was going something like this, and the dissipation rate were going something like this. The production rate of turbulence kinetic energy and the dissipation rate of turbulence kinetic energy. This is how it was looking like. Okay, this is your wall normal. Let's say this is the y direction here. So on the wall at y equal to 0, epsilon will be epsilon maximum in a wall bounded flow. Okay, so dissipation rate becomes maximum on the wall. Okay, so this is your typical budget that we looked at, right? Budget of your turbulence kinetic energy, if you look at. So now we say that to first order there is no y dependency in the near wall zone, but then we see that epsilon becomes maximum on the wall. So how do I specify a boundary condition? Therefore, how to specify epsilon wall boundary condition? What we do now is that we take the help from K equation, because turbulence kinetic energy has both exact equation and model counterpart. So we take help from K to see whether epsilon boundary condition can be given. Okay, so to proceed further, we take help from turbulence kinetic energy equation, because both model and exact terms exist for TKE. For epsilon we only have model terms. The exact equation exists, but we did not model that, right? So therefore we start to take help from the turbulence kinetic energy equation. Okay, so as y tends to 0, what will happen to your K model equation? So consider K model equation, okay, which is dou K by dou T plus uj bar dou K by dou xj equal to, I have the diffusion term nu plus nu T by sigma K dou K by dou xj plus Pk minus epsilon. Okay, Pk also I can expand it if you want. So Pk term is 2 nu T Sij bar minus 2/3 K delta Ij dou Ui bar by dou Xj minus epsilon. Okay, this is your production rate, diffusion rate terms. So now in this we are going to consider again the sublayer, right, as y tends to 0, that is in the sublayer zone. We are looking at a zone which is very close to the wall. So in this, and then considering the same conditions as before, a statistically stationary, homogeneous, right, same conditions as before, statistically stationary, homogeneous, homogeneous means statistically homogeneous, statistically homogeneous along x comma z, same conditions, fully developed, also fully developed, same flow conditions we are using for a turbulent boundary layer in a very thin zone close to the wall. If I do this, then this equation here, it's called this 1, equation 1 reduces to a simple form. So the entire left hand side is 0. So to this particular equation would result in, I would get, so as you approach wall, okay, so this is approaching, so I would use approximate here to first order. Nu t here, what will happen to nu t on the wall? Eddy viscosity on the wall 0, right, k square by epsilon, k goes to 0, eddy viscosity has to go to 0, right. As y tends to 0, eddy viscosity will be 0 here. Nu t also approaches 0. So that means to first order, this turbulent diffusion term is removed, nu t by sigma k dou k by dou xj. I will essentially have equation which is dou by dou x1, dou by dou x3 are also gone because of the homogeneity, only dou by dou x2 term which is dou by dou y, right. So I will get dou by dou y term of nu dou k by dou y. This term exists. The viscous diffusion rate will be dominant in the linear sublayer and little bit above that zone, right, in a sublayer. And then what will happen to the production rate then? Nu t is going to 0. So the last term here, this particular term, delta ij dou I by dou xj, by continuity it is 0, right. When I equal to j, dou ui bar by dou xi, so it becomes 0 because of continuity. So I have essentially 2 nu t sij bar dou ui bar by dou xj, and nu t approaches 0. So to first order it is dropped. So pk is 0 production rate, and we also see from data, in a very thin zone very close, production rate is nearly 0, epsilon goes maximum. The viscous diffusion rate is also large. If I am going to write viscous diffusion rate, it will be large. Viscous diffusion rate will go like this. Okay, this is your viscous diffusion rate, which is nu, or this term nu dou square k by dou y square, the viscous diffusion rate, that will be large. So this term survives and the dissipation rate survives. So to first order, I am going to get this simplified equation here, okay, in the sublayer as y tends to 0, and therefore I can set a boundary condition here, epsilon wall will be equal to nu dou square k by dou y square. I can set this as the boundary condition. This boundary condition has one problem. Anything that you will notice here, the CFD experts should know what will be the problem here implementing this boundary condition. This is one option, okay, you can say option 1 here, boundary condition option 1 for epsilon wall, right. So what is that you think? What will be the problem implementing this? Yes, there is this a second order term is sitting here. Okay, the order of this term is, it's not dou k by dou y, it's dou square k by dou y square. So this will be numerically unstable. If you implement it in your assignments, you can see that it will be unstable, very difficult to get convergence. Okay, so this is numerically unstable. Unstable because you have second derivative on the wall. This condition can be implemented, but it will be numerically unstable. The Neumann condition, as Nirupam suggested, that is also possible, but it will not give good results. Okay, so you need to make it go maximum. It may not go maximum. If you specify, the code may work, but you will not get good results. So then that means we need to search for a condition which is numerically stable, okay, and also gives reasonably good result. For that, we go and take help from the epsilon exact term, because there is, if you ignore the transport equation for the epsilon model, the epsilon itself has an exact term in the turbulence kinetic energy equation, right? So we can take help from that. So an option 2 is, say, boundary condition option 2 is, we take help from the epsilon exact term is nu dou ui prime by dou xj dou ui prime by dou xj over bar. This, if I expand, it is a sum of 9 terms, right? So I get nu dou u1 bar by dou xj dou u1 bar by dou xj plus nu dou u2 bar by dou xj plus nu dou u3 bar and then j is also repeated, so Einstein summation again. So I would get sum of 9 terms, so which will be, if I modify in the same equation, or let me write it down. So 1 1, let's say, then I would get the other terms, dou u1 prime by dou x2 dou u1 prime by dou x2 average plus nu dou u2 prime by dou x2 average plus nu dou u3 prime by, sorry, dou x2 sum over j, and then of course extra 3 terms for summing over the u1 prime x3 plus nu x3 plus nu u3 prime dou x3 sum of 9 terms. Now we consider again in the near wall zone. Okay, so when you go to near wall, that is as y tends to 0, okay, we consider, let dou by dou x2 term will be much larger than dou by dou x1 or dou by dou x3 terms. The wall normal gradients will be much larger than the wall parallel gradient. in the sublayer, okay, in the sublayer. In addition, the wall parallel fluctuations will be much larger than the wall normal fluctuation. We already saw two component limit, right? VRMS is much smaller than the URMS or the WRMS. Therefore, in addition to this, we will have the U2 prime or sorry U1 prime comma U3 prime will be much larger than your U2 prime in the sublayer zone. Okay. So, if I use this consideration, then this particular equation here, now this will be only this dou by dou x2 terms, the 3 terms here will be important. In that, the U2 prime will be omitted. So, this approximately becomes only this particular term, this one and this one. So, this will be nu dou u1 prime by dou x2 dou u1 prime by dou x2 average plus nu dou u3 prime by dou x2 average. All others are higher order terms here. Okay, is this clear? So, we are considering the wall normal fluctuation to be much smaller than the wall parallel fluctuations, and the wall normal gradient is much larger than wall parallel gradients. So, only dou by dou x2 gradients are much larger, and in that u2 prime is much smaller than u1 prime and u3 prime. So, I get this equation. So, epsilon exact will now therefore be epsilon exact is now approximately equal to, if I write in the XYZ or UVW formulation, I would get essentially nu dou u prime by dou y dou u prime by dou y plus dou w prime by dou y dou w prime by dou y. So, what is dou u prime by dou y? When we did a Taylor series expansion, dou u prime by dou y, and we set it as some a1, b1, c1, something of that order, right? So, dou u prime by dou y is the a1, dou w prime by dou y is the c1. So, I can write this essentially as, so epsilon, I would write this as nu of a1 average, it is a correlation term, plus c1 average, or can write this as a1 square average plus c1 square average. Let us call this equation 1 here. Okay. So, now we take turbulence kinetic energy K, which is half of u prime average plus v prime average plus w prime average. Again here same condition, the VRMS has to be much smaller than the u and the WRMS, right. So, this is, we can say, approximately equal to half of your u prime bar plus w prime bar. This is a much smaller term, right, in the near wall zone. So, that implies K now is equal to half of the u prime square. So, this is nothing but, again, if you look at what is u prime, it was a1 y to first order, right. So, it is a1 y average, which is a1 y a1y average plus we have c1y average is equal to half of a1 square average y square plus c1 square average y square. Okay, or I can write this as y square by 2 a1 square average plus c1 square average, equation 2. I need to give boundary condition for epsilon here on the wall, okay, and the k is known to me. K boundary condition is 0 on the wall, and everywhere I am computing for k, okay. So the epsilon boundary condition here will be, if I make use of equation 1 and 2, equation 1 comma 2 gives me essentially epsilon is equal to nu this a1 square plus c1 square bar, that particular term can be replaced by 2k by y square. Okay. So you have your boundary condition for the wall, but if you implement it on the wall node, then k is 0. So you should not implement this on the wall. I did mention in the Low-Reynolds number the boundary condition P node, first node above the wall. Okay. For all other things u bar, v bar, w bar, that is for the south node. This is south node, you can implement here. South node or the S what I have written here. Okay, the wall, on the wall, this particular node here. So that you can implement. Velocities can be go to 0 exactly on the wall node, k goes to 0, you implement your Neumann for pressure, no problem, but the epsilon boundary condition is for the P node, first node above the wall. Don't implement epsilon boundary condition on the wall. It should be first node above the wall where it is y plus less than or equal to 1. Okay, this is important. That's the wall boundary condition for your epsilon. So this is epsilon. So you can write it here, epsilon, which is the first node above the wall. Okay. First node above wall, then only k will be non-zero, and we have a magic here. Epsilon had no y dependency, but now suddenly it is 1 over y square dependency. As you approach wall, suddenly you get epsilon very big, right? Now you see suddenly it has 1 over y square behavior, right? 1 by y square behavior. For modeling, right, the exact one doesn't have, but for modeling idea it is coming as 1 over y square. So as you approach wall, epsilon will increase. Okay. So this is one good condition that can be used, option 2.